A drone is flying through a room. It has high-definition cameras, complex security software, and a full battery. Yet it misses a flat white wall and slams into it. The system was so busy processing heavy security code that it couldn't actually comprehend the space it was flying through. To fix this, we need to restructure empirical robotics. We are moving away from traditional rigid programming and instead borrowing a specific set of tools from Hollywood visual effects artists. Grab a piece of paper and a pen. We are going to draw a new blueprint for a machine that is built to understand its environment rather than just react to it. By replacing blind algorithmic guessing with a VFX-inspired visual framework, we can build robotic systems that are responsive, secure, and easier to troubleshoot. Step 1 starts with the eyes. In the center of your paper, draw a simple robot. Now draw a cloud of floating dots completely surrounding it. These dots represent 3D camera tracking, or VSLAM. On the left, you see what a standard robot sees, a flat 2D photograph. On the right, we overlay a dense 3D tracking point cloud. This maps the exact physical geometry of the room. Think of these tracking points as invisible strings stretching from the robot to every surface. They provide the machine with the precise mathematical distance to the wall, to the floor, and the ceiling. Many robots use a black box AI to guess the depth of their surroundings. VFX tracking avoids guessing by forcing the robot to measure and follow the actual laws of geometry in real time. With these VFX eyes, the machine stops making estimates. It now operates using a precise coordinate map of its entire physical environment. For step 2, draw a protective shield or an umbrella directly over your robot. Vision is powerful, but cameras can be blocked by dust or disabled by external interference. When the primary sensors fail, we need a survival protocol called Resilient Systems Engineering. We use drift correction. If the camera is interrupted and the eye flashes red, the system reroutes navigation to internal gyroscopes. This keeps the hardware balanced, like a person who is suddenly blindfolded using their inner ear and a cane to maintain their stride. Engineering resilience is not about preventing all sensor failure. It is about designing a system that can automatically compensate and maintain its capability when that failure happens. For step 3, draw a small radio antenna and a padlock next to your robot. Heavy security software often creates latency and drains a robot's battery. We need a way to secure data without weighing down the hardware. We start with paradigms frequencies. This chart shows how complex systems operate on distinct rhythms over time. By tracking its internal logic's frequency, the robot creates a signature of normal behavior, allowing it to instantly filter out erratic noise from hackers. Once the signal is verified, we apply lightweight cryptography. This secures the data with minimal power, ensuring the robot stays protected without sacrificing reaction speed. Combining this frequency filtering with a lightweight lock creates a secure, secret language for the robot that works in real time. For the final step, draw dashed lines connecting your robot to a cloud icon at the top of the page. To manage the robot's intelligence, we use Kaizen paradigms, a philosophy of continuous incremental improvement. When the robot encounters a new problem or makes a mistake, it doesn't just store that data locally, it beams the experience up to the cloud. Using a serverless architecture, this transfer is instantaneous. One robot node sends up a red error packet. The cloud calculates a fix and fires back a green update to every robot. This feedback loop ensures the entire fleet learns from a single unit's mistake. By linking Kaizen with a serverless cloud, the robot evolves from a static machine into a connected intelligence that improves every single day. Look at your completed drawing. You mapped out a decentralized, multi-layered framework for a resilient robot. You gave it VFX tracking for sight, resilient engineering for survival, frequency intelligence for security, and a serverless cloud for its brain. This is how we restructure empirical robotics. We have a system engineered to be resilient and self-correcting in the real world. If you were building a robot with these VFX eyes, what is the first environment you would want it to map? Let me know in the comments. Subscribe for more deep dives into resilient engineering. Stay sharp.